Okay, so there's a bunch of different ways to access this information. There is, of course, a table of contents, which is very paper-like. It's just a list of the experiments. But there's other ways to find it. Since this is the Cheminformatics theme here, I'm going to talk a little bit about inchies and inchi keys. So we use inchies for most of the small molecules, and we've been using more and more inchi keys for the larger molecules, because we want our compounds to be found in Google. And it turns out that the inchies for the larger molecules, let's say 500 Daltons, they don't actually get indexed properly in Google. So the inchi keys is basically just a hash of that. They look like this right here. No matter how big the molecule is, the inchi key will be the same length. So that actually gets indexed really nicely by Google. And you can do even Google custom searches. So that's a free service that Google offers. You could say only search this domain, and so you can so you can actually you get a lot of free flexibility with Google, and that's it right here. So what I'm doing here is I'm searching for this the first part of the inchi key. Basically, the way, if you're not familiar with the inchi keys, the first part gives you the connectivity of the atoms, and the second part gives you the stereochemistry. So if you only search for the first part, you're sure to get all the isomers. Okay, so some other ways that people might be finding our experiments. Well, these are some of the search terms that I just looked for about a week to see how people were doing this, and there's 4 basic categories. First are specific compounds. So someone will search for methylene chloride or tosyl isocyanide, or they'll be searching for experimental conditions like kinetics of Bhakti protection. We've actually done a lot of NMR monitoring of the removal of the Bach group. So if you're looking for that, you're in luck, because you've got piles of data that you can grab. People are also looking for general educational stuff, like how to make a poster in Second Life or 3D periodic tables. Those are some of the things that appear on my blog, for example. And of course, big picture things like Cheminformatics project proposal. And I actually put my proposals up publicly, so if people want to see what we plan on doing, they can also grab it through there. I'd like to give you an example, actually, that's just like 2 or 3 weeks old, which I think is a great way to actually show how a wiki can be used. This is a search that someone from the UK did, purification of phenylacetaldehyde. And the first hit from that Google search is our experiment 37. When you hit that, it turns out that it's one of my undergrads, James. And the title of this experiment is purification of phenylacetaldehyde, and he's doing a distillation. So let's go through the experiment and see what happened. Okay, so you find this procedure. All right, simple enough. And he took a picture, so I can actually see where the thermometer is. I can see exactly what's going on. He put up an NMR. Now this is before we started to use JCamp, so this is not expandable. This is just an image. And you can see that there is some stuff going on here. It does look like it is phenylacetaldehyde, but it's certainly not the purest compound that I be happy with. And of course he has his log, so I can see exactly how long everything took during the distillation. So if you look at the discussion, actually it's not so simple, right? Because he reported the distillation happened at 162 degrees, but the reported boiling point is 195 off this reference, this MSDS sheet. So there's something strange going on. And so the conclusion is that we can't use this distillate. In fact, there were globules of liquid inside of it. Okay, so basically, I don't know, maybe we're the only people in the history of the world to have this problem with phenylacetaldehyde, or maybe not. So this might be helpful. Now let's take a look actually at the real power of the wiki. What you just looked at was the final state of the wiki, but let's see the history, how it actually came to be that way. So this experiment started in October 27th, 2006. And the wiki history gives you all the different people who modified it. And if I click on that first entry, you'll notice here that the conclusion is different. It says phenylacetaldehyde was indeed purified with only little traces of impurities. So something happened between this and what it looks like today. And we can see the difference between the different versions. So October 29th, I actually modified it. And the way it works on Wikispaces is the green stuff is the added and the red stuff is the deleted. So you know from this that I deleted his conclusion and I put this conclusion that, in fact, it wasn't good. It wasn't a good distillation. And there's a lot of that kind of thing going on with our wiki. It's a very good way for me to interact with my students. In this particular case, I actually wrote the answer, but often I will actually pose a question. I'll say something doesn't make sense, maybe look into this NMR a little more, and that actually is a really good way to interact. Looking further down, in June, my graduate student came in and put a link to the ChemSpider entry, and he also added tags. So he added the INSHI tag. And then actually a year later, James answered this question. If you remember that picture, right, there was no tubes attached to the condenser. I thought that was a little weird. So I asked him about it, and he said that actually that picture was not of that run while it was happening. So he answered the question. Now, we can keep going on like this till infinity, right? And that's really what research is really like. And it's sort of a fiction to think that we do research, it stops, and it turns into a fact. And then it becomes a paper. But that's not really what happens, right? We keep at this process until we feel comfortable enough to put it in a paper, but we're never completely satisfied, right? And this really captures that whole process. And so students can actually write reports on what they did, and they can link to their own experiments, and they can actually link to their lab mates' experiments very nicely. So here Shannon is writing a report. She's comparing her results with Emily and with Tim, and there's no confusion whatsoever who did what, because the wiki captures every single addition from each one of the students. And that's something that I really like in terms of, if I need to assess a student, I can tell what kind of discussion did they write, did they do conclusions, did they do the experiment. So real quick, I'll just basically go through the other ways of getting to that information. So far I just used the wiki, I just used Google, but that's not really the perfect way to get to this information, right? Because we're repeating the same reaction, this Yugi reaction, and we keep changing the conditions slightly. Wouldn't it be nice to be able to compare all the reactions in one place? And we use a Google Doc for that, where each one of these experiments has all the entries in the table. So I could go to this table, I could sort by the amount of acid, and then this will link back to the wiki page. So if I wanted to dig deeper, I could. Okay, so remember, this does not have all the information. A table can never completely represent an experiment. We pretend it does in a paper, but in fact, every table and every paper that's ever appeared should have an asterisk next to each entry because it was a little bit different than the other one. This allows you to do that in complete honesty, because if you want more information, you can just click back to the wiki. So that's another way. Another way that we can spread our information is with CDD, Collaborative Drug Discovery. Once we do our antimalarial assays, we can report the assays on this database. And this is publicly available as well.